Introduce Simon Ritter, Deputy CTO of Resource Systems, who's going to take us through tonight's presentation. So I'm going to start sharing here. And oh, there's a chat. It was behind the share thing. And Simon's going to start sharing.
Okay.
I believe.
Yeah, let me find the right. See if there's the right one. Yeah. Yeah. Okay. Now we go here. Okay. So hopefully you can see my slides.
Yep.
Yes.
Good. Okay. Excellent. Right. So Java at speed, building a better JVM. So what I'm talking about, obviously, is how do we change the JVM to get better performance? And the first thing I did when I started looking at doing this presentation was to think about what do we actually mean by speed in the Java world? Because the key thing here is that we're dealing with the idea of the JVM, and that introduces this layer between our application code and the machine that we're actually running on. And that's a bit different to where we've got statically compiled code, because that's just native instructions executing on a machine. And so what we've got to consider is how does the JVM impact the performance of our application? And I thought to myself, okay, let's draw a graph of what we would like in terms of the ideal performance of the JVM running an application. And I came up with this very complicated graph that looks like this, which is essentially a nice flat line, because that's really what we want. We want 100% of the possible performance from the JVM right from the beginning, and then all the way through when we're running our application, we get 100% of performance. So that's obviously what we want, and it's the ideal. But the problem is if you look at your typical JVM running a typical Java application, the profile will look something different, and it will look much more like this. So we start off slow and we gradually warm up and we get to a level of speed that we want. If we dig into this in a bit more detail and try and understand what's actually going on, then we can look at how we can change that to improve the performance of the JVM. So at the beginning, when we start our application, the thing that we've got to consider is that we're dealing with bytecodes. And the obvious thing here is that bytecodes are instructions for a virtual machine, hence the Java virtual machine. So what we need to do is we need to convert those bytecodes for our virtual machine into instructions for the real machine that we're actually running on and the operating system that we're running on. That's interpreting. And the way that that works, and this is how Java started out with its virtual machine, is every time we see an instruction, we convert it into the necessary instructions or system calls for the actual machine that we're running on. And we do that every time we see the same instruction. So we don't do anything clever in terms of caching things or compiling things or anything like that. So the effect of that is it's very inefficient and it's very slow compared to natively compiled code. That's one of the reasons why when Java was first released, its big criticism was it's slow compared to C and C++. Having found out that that was a bit of a problem, the developers of Java said, okay, how can we solve this problem? And they looked around and they said, okay, there's this thing called JIT compilation, just-in-time compilation. Let's have a go at that. And so what happens now is that we start off running in interpretive mode, and the JVM will keep a track of how many times you call each method. When a method gets to a certain threshold, where it's been called enough times, the virtual machine will say, okay, that's a hotspot of code, hence the name of the JVM. What it will do is it will then pass that method to the JIT compiler. In this case, it's the C1 JIT compiler, it used to be called the client JIT compiler, and that will compile it into native instructions. That will then run faster because clearly we're not having to interpret every bytecode every time. Now, C1 JIT compiler is designed to compile code as quickly as possible, but it doesn't really do a lot of optimization in terms of improving the flow and the analysis and so on of the code. So we see a gradual improvement as more and more methods are compiled with the C1 JIT compiler. One of the other things that the C1 compiled code does is to collect profiling information about how that method is being used as it's running. And that way, when we keep track of how many times the method is called, at some point we'll get to another threshold, and that's when we will then recompile that method, because it really is a very frequently used method, with a different compiler. And we'll use what's called the C2 JIT, or used to be the server JIT. And so that will then use the profiling information that we got from when we were running with C1 compiled code to use a different compiler that applies a lot more optimizations to the code that we're generating. And that way we get much better performance for it. So if we look at the way the graph warms up, obviously more and more methods get compiled with C1 and then get compiled with C2. But we also see some big dips in performance. And that's down to what's called de-optimizations. The reason for that is that one of the things that the C2 JIT compiler can do is use speculative optimizations. Speculative optimization essentially says that if we look at the way that an application has run up until this point, let's assume that it will continue to run in exactly the same way in the future. And simplest example of that is if we've got an if statement, and all the time that we're running our application, we only go through the true branch of that if statement. What we'll do is we'll assume that in the future, we'll only go through the true branch of the if statement. So we'll optimize that code and eliminate, in effect, the false branch. At some point, we may decide that, well, we may find that in terms of the way the application code runs, suddenly we do actually need to go through that false branch. Now, that will still work, but what will happen is we'll get a de-optimization. The JVM will say, oh, hang on, we compiled it based on only going through the true branch. Now we've got to throw away that code because it's wrong and recompile it, assuming that we can go through both branches of the if statement. So those are de-optimizations. Those are very bad. We want to eliminate those as much as possible. What we'll then find is at some point we'll get to a steady state, so our sort of 100% level of performance. And that's where all the frequently used methods have been compiled, we've gone through all the de-optimizations and so on. But what we'll still find is that there are dips in performance. So we'll see some significant degradation. And that's due to a different thing. That's due to garbage collection pauses. I'm sure anybody who's written in Java of any sort of size will be familiar with these things. So what we need to do is figure out how we can solve the issues around this particular set of sort of circumstances. So the challenges that we're dealing with here are primarily because the JVM provides us with a managed runtime environment. Now, that's really good for us as developers because it eliminates a lot of the things that we would normally have to do in other languages, and we can just let the JVM handle that for us. But if we look at the two specific things that are significant, first of those is garbage collection. So the JVM handles memory management for us automatically. It allocates space in the heap for our objects. It then reclaims that space when we no longer have references to objects. Problem is that the way that the garbage collectors work, and in fact any garbage collector, is inherently non-deterministic. We can't predict with any accuracy when the garbage collector is going to run or how long it's going to run for, because we don't know how frequently we're going to allocate objects or how frequently we're going to get fragmentation in a heap and things like that. So that non-deterministic nature makes it very difficult to sort of account for it when we're tuning our applications. The other thing that we find with a lot of garbage collection algorithms is that pause times can be very big. And that's down to the way that the garbage collection algorithms work. And you may see garbage collection pauses that could be, hundreds of milliseconds. You could be seeing seconds of pause. Maybe if you're very unlucky, you might see some minutes of pause. The longest garbage collection pause I came across was a company, a customer that I was talking to in the US. I won't say who they were. And they had a garbage collection pause of 1.5 days, which is quite extreme, really. And when I was talking to them, I said, well, how do you even know after a couple of hours that it's still doing garbage collection? Hasn't it just stopped? And they said, no, we've got JMX instrumentation and we can see that it's still doing stuff. And so we just let it run. And so I said, well, surely it just makes more sense to stop the application at that point and then restart it, because you can just avoid that whole 1.5 days. And they said, no, actually loading the data and processing the data to get this application running takes more than 1.5 days. So it's actually better for us to wait 1.5 days for a garbage collection pause. they were very happy when we showed them Zing, because of course that the whole idea of eliminating garbage collection pauses. The other thing that we deal with, as I've said, is bytecodes, not machine code. And the issues there are the fact that we have different strategies around adaptive compilation. And it's this speed of warm-up that's the thing that we also need to think about, because that happens every time you start an application. So what we like to say is, what if there was a better JVM? And the answer is there is. So it's Zing. Now, don't worry, I'm not going to be doing a sales and marketing pitch here. What I'm going to do is I'm going to explain how Zing works from a technical perspective, so you can make your own mind up as to whether you want to try it for your applications and so on. Now, if you look at what we've done with the Zing JVM, when we decided to try and address the issues of performance, we said, okay, let's not take the approach of starting from scratch. Let's not rewrite the whole JVM, because a lot of it works very well. We don't need to write everything from scratch. So we'll start with OpenJDK, open source for the Java platform. And then we'll change some bits of that we think could be improved. Once we've done that, we built our new JVM, we'll run all of the TCK tests on that to ensure that it complies with the standard defined by the JSR for Java SE. Now, the good thing about that is it means that it's not special from the point of view of Java applications, meaning that you don't have to change your code. You don't have to do anything special in terms of your application to make use of the way that Zing works. You don't even have to recompile your code to take advantage of different ways that the compiler works. So it is very much a drop-in replacement for other JVMs. You can simply take your existing jar files, your existing class files, point them at a different Java executable, and everything will run in exactly the same way. You just get better performance. In terms of what we've changed, we've gone to 3 different areas. So the first of those is replacing all of the collectors in hotspot with one that we call C4. And I'm going to talk through what it is that we actually do with C4 and how it works in the next part of the presentation. One of the things that we also did with this was to look at how the JVM interacts with the operating system. And specifically, we looked at the Linux platform, and we decided that there were some interesting things that we could do in terms of modifying the way that the operating system itself works. So this means that Zing is actually only supported on Linux. The reason for that is that we have these things called Zing system tools, which sit at the operating system level and handle memory allocation for the JVM. Again, I'll talk more about that in a moment. More recently, what we've done is to replace the C2 JIT compiler with one that we call Falcon. And that uses a different approach to how we generate the compiled code. We can do some clever things with that. And again, I'll explain that later on. And then the last thing that we've done, which is more sort of complementary to the JVM, is the introduction of what we call Ready Now as a warm-up elimination technology, so that we can minimize the time it takes to get from starting off with interpreted bytecodes and going through to heavily compiled, heavily optimized Falcon compiled code. Talk a little bit more about the Zing system tools. As I said, it sits at the kernel level in the operating system. And as I say, what we did was we looked at the way that the Linux virtual memory system works, and we said, okay, that's a very good approach for general applications, but the JVM is a very specific application. And we thought we could do better in terms of providing a way of mapping from physical pages of memory to the address space of the JVM and doing some clever things there. So one of the things we do right from the beginning was returning memory from the JVM to the kernel. So if you've got other processes or other JVMs running, then you can make better use of the resources you've got in the machine. The other thing that we do is keep a much tighter view of the cache status and cache lines that are available. So we know that when a new page is required for allocation of more objects, then wherever possible, we can give you a hot page that's already in cache, and therefore you're not waiting for that to load from memory and delaying the use of that page and so on. We can do some other clever tricks with these things. One of those is what we call contingency memory. And the way that the Zing system tools works is that in order to be able to manage memory for the JVM, we grab a large amount of memory, typically when the machine boots. You can configure it in different ways, but by default, we grab a load of memory when the machine boots and make that available for the JVM. What we'll do is keep some of that memory aside as contingency memory. That way, if you've got a JVM that is using a heap space of, let's say, 8 gigabytes, and you start your application up and it runs quite happily, no problems at all. Suddenly you get hit by a very heavy load, lots of transactions coming in, and the usage goes all the way up to 8 gigabytes. Now, with a normal JVM, if you get up to your 8 gigabyte limit and you try and allocate another object, it's going to stop. You're going to get an out of memory error and you get an abrupt termination of your application. That's not very good if it's a mission critical application. What we'll do is, assuming that we still have some contingency memory left because it's not infinite, we'll allocate some of that contingency memory to that JVM. We'll allow you to go beyond the 8 gigabyte limit that you set. That way you can still allocate objects, you can still continue to run your application. We will then get the JVM to run the garbage collector more frequently and do more work to try and bring that back below the 8 gigabyte limit that you set. And we'll send you lots of messages on the console and the log files to say, look, this happened. You may want to increase the heap space for this particular instance. But it tries to avoid the problem of getting an abrupt termination of your application. Okay, let's talk about how we actually do the garbage collection in Zing. And as I said, we have this thing called C4, and that stands for the Continuous Concurrent Compacting Collector, which essentially describes exactly what it does. It's a collector that runs continuously in the background. It is fully concurrent, and that's very important because all phases of the garbage collection algorithm run concurrently with application threads. There are no stop the world pauses in the algorithm. So you will not see any pauses as a direct result of all threads having to be paused in order to do garbage collection work. Having said that, it is a compacting collector, meaning that we will relocate or move objects around the heap in order to eliminate fragmentation and make the objects that you're using contiguous in memory so that we can do better memory management for those things. And of course, it is a garbage collector. Now, from a basic point of view, C4 uses similar approaches to other algorithms in certain parts of it. So one of those is the way that we designed the heap, and the heap is generational, meaning that we divide it into two regions, young and old. Now, that's a very common thing that garbage collection algorithms do. And the reason for that is that you've got this thing called the weak generational hypothesis. And that says that most of the objects that you're going to allocate in your application will only be used for a very, very short space of time. So literally, within a few hundred or few million instructions, your objects will no longer be used. Within the time that it takes to allocate another megabyte, most objects will no longer be used. So if we organize the heap into young and old generations, by collecting a lot of the objects in the young generation, we can reduce the load on the old generation and make that more efficient as well. All of this, as I said, is fully concurrent, and all of the phases are also parallel, meaning that we can apply multiple threads to the work and therefore minimize the time that it takes to actually complete each of the phases that we're doing. And as I said, it's compacting. Key thing, as I've said, is that we don't have stop the world pauses, and we do not have a compacting fallback. If you look at things like CMS and G1, parallel collector, all of those at some point will say too much fragmentation in the heap. We need to do a full compacting collection, and that's where you do see these very long pauses. In terms of the way the algorithm works, it's a three-phase algorithm. It's mark, relocate, and remap. So how do we do this? How do we actually enable garbage collection to happen at the same time that your application threads are still doing their work? And the kind of key thing for that is what we call the loaded value barrier. And this is essentially a read barrier. meaning that every time you access an object, we will intercept the reference to the object header, and we will do a little bit of work to understand what the state of that object header and the object is. And if need be, we'll redirect to some code and we'll update some things and then pass the reference back to you. By doing that, we can enforce two rules. The first of those rules is that if we're in the marking phase of the algorithm, every object that you get will be marked as valid and live data. And that means that you will never have the situation where you will accidentally have an object that you're using garbage collected because it hasn't been marked. So that's the first thing. Second thing is that when we're in the relocation and remapping phases, we will always guarantee that the reference you get to the position of that object will be correct, from the sense that you can make changes to it and those changes will not be lost. So if we haven't moved the object yet, you get the old reference. If we have moved the object, you get the new reference, and there's no issue with getting caught in between and making a change to the old reference, even though we copied it, and losing the changes that you make. So this does allow us to do fully concurrent marking, fully concurrent relocation. Now, often people say, well, hang on, if you're intercepting the read to every object, we do lots of object references. Isn't this going to degrade performance by placing an extra load on every reference that we access? And the answer to that is, well, yes and no. So what I mean by that is, yes, it does introduce a slight overhead, but essentially what we're doing is using some of the bits in the object header to determine what the state of that object is in relation to the phase of the garbage collector. So we can do that in a very simple way as two instructions, which is test and jump. We test the bit that we're interested in. If it's not set in the way that we want it to, we can jump to a handler, we can do the work that's necessary, return, and then set the bit and pass it back to the application. Most of the time, we're going to find that that bit is in the right state, so we don't have to do any work, and then we can simply pass the object back to the application. So taking those two instructions, and you look at what that equates to in terms of the microcode at the processor level, and it's a single micro operation. So the overhead for an object reference is less than 1 nanosecond. Still, you might say, well, lots of references impact, but we've of this. The overhead, once you go beyond L1 cache, once you're reading L2 cache or L3 cache or main memory, then the time it takes to make those memory accesses is far more than the overhead of our test and jump. So literally, you would have to write an application that only reference memory or application values in L1 cache. And at that point, you would see a degradation of somewhere between 0.5% and 5%. But nobody writes applications that only run in L1 cache. So how do we do this? Okay, so in terms of the marking phase, what happens is we decide at some point that we need to do some garbage collection. So the JVM will keep track of how much free memory there is, and it will say, okay, time to start doing garbage collection. And at this point, again, we follow the same sort of approach that some other algorithms take, which is to generate a root set. And the root set is a list of all the objects that you have directly accessible from your application code. To generate that, we will scan the stack, we will look at the registers, we will look at static variables, and we'll build up that list of objects. Obviously, many of those objects will reference other objects, and then those objects will reference objects and so on. So we need to use that root set, and we need to trace from it to build up the complete graph of accessible objects from the application code. To do that, our garbage collection threads will start work, and they will look at the root set object, and the first thing they will do, they will set the bit in that object header to say, this is an object that's in use. Then it will follow the object references from there and it will mark any objects that it finds, and it will continue to follow through references all the way through the graph until it's followed all the links and comes back to the root set. Now, there's no problem with that root set in terms of contention, so we can actually do that in parallel very easily. We can decompose it into multiple threads and have the work performed in parallel. That will work quite nicely. Obviously, at this point, the application threads are still running. So if we get to a situation where an application thread references an object, as I say, we'll use our test and jump. We'll look at the bit in the header to say, has this been marked as an object that's still in use? And if the case is that it isn't, then at that point, we'll jump to the handler. The handler is just a small bit of code that will mark that bit, set the bit to say that this is an object in use. So we guarantee that that object is going to be marked. Obviously, we still have to trace any object references from there, but we don't want to do that in the context of the application threads, because that could take quite a long time if it's a very complicated graph. To get around that, we simply pass the object to the garbage collection threads and say, make this part of the root set and let the garbage collection threads follow the links for us. If we were to make a use of another object from there that didn't have the bit marked, we'd do the same thing in terms of the test and jump, and we'd mark it. So we guarantee, as I say, that during the marking phase, any object that you get as a reference will be marked as valid, and so it won't get accidentally garbage collected. We then need to go to the relocation phase. And the idea here is that in our heap, we've got objects dispersed and we've got fragmentation, gaps between them. And we can see in this example here, we've got 5 objects, A, B, C, D, E, and we need to relocate those to make them contiguous in memory. So what we're going to do is we're going to simply say, okay, let's copy those objects from their current position to empty space in our heap and effectively compact them. That's pretty straightforward. We can simply say, okay, let's copy A to position A prime, B to position B prime, and so on. And that ends up with the objects being contiguous in memory, eliminating fragmentation. In terms of allowing the application threads to run concurrently, when we're doing the copy, we will place a lock around that. So when we're copying object A to A prime, we'll lock A so you can't reference it, you can't make any changes. So technically that does introduce a pause, but it's not a stop the world pause. It's a very small pause, basically the amount of time it takes to copy object A to A prime. And since most objects are very small, they're only of the order of kilobytes, it takes literally no time at all. Well, not no time at all, but a very short amount of time to make that copy. So the effect of the block on the thread is going to be very minimal. What we then do is, in addition to copying those objects, we create a side table. And the side table is essentially a list of where each object has been relocated to. So A has been moved to A prime, B has been moved to B prime, and so on. And there's a very, we have a very obvious reason why we want to use a side table, because some other algorithms use a thing called a Brooks forwarding pointer, which essentially puts a pointer inside the object itself, so you can tell whether it's been relocated or whether the object is where you think it is. We don't do it that way. We put it in a side table. And the reason for that is what we call quick release. And this is another one of those things that we do with the Zing system tools. So the Zing system tools, because we manage at the operating system level the mapping between the physical pages and the virtual address space of the JVM, we can do some interesting things. So here what we can say is that in order to garbage collect any heap of any size, we only need 1 page free per garbage collection thread. And the reason we can do that is because if you look at the picture here, we've got 1 free physical page that we put at the bottom there so that we can copy the first set of objects into that green page on the bottom. Now, when we want to copy the next set of objects into the next virtual page, we need to find a physical page to put underneath it. But if we've only got 1 free page and we've already used it, where can we get one from? And the answer is that on the top line there, because we've copied the first 2 objects, we know that we will never, ever reference those objects again. Not going to happen. So we can actually steal the physical page from underneath that virtual address space. Even though technically it's still associated with the process, we know we're never going to use it. So we steal that page, map it to a different virtual address space range, and then we can copy the next set of objects into that space. And then when we need another free page, we can steal the next one. So this is essentially hand over hand reclaiming space, meaning we only need one free page to start with, and then we just keep going, stealing each page as we need it. Having done all of that, we then need to do the remapping, which is where we need to update the object headers to say this is the new reference for where the object is going to be, and making sure that obviously when the application wants to use it, it gets the right place to update the data. So again, what our garbage collection threads are going to do here is to work its way through the table and say, okay, A has been moved to A prime. So we will go to that object header. We will update the information so it's now correct. And then we'll set the bit to indicate that we've done the update. We can do that in parallel, because again, there's no contention. So we don't need to worry about the problems of decomposing that into multiple threads. If the application, which is still working, references an object, then what we do is we go through our test and jump again, and we look at the bit to indicate whether this object has been updated. And if it hasn't, then again, we jump to our handler, and that will then effectively do the work of the garbage collector in the context of the application thread, use the side table, find out what the reference has been changed to, update the object header, set the bit so we know next time we want to use this object, it's already been done. Even the garbage collector will know it's been done. And so pass that back to the application thread, and we know that we've got the right address for the object having made the move. So we always guarantee that you get the right reference to the object, and you can make updates without losing any of the changes to your data. So this means that we can work with very big heaps. Big heaps, no problem. So essentially, we can scale all the way up from 512 megabytes as a minimum, all the way up to 20 terabytes in heap size. And you won't see any degradation in pause times for garbage collection, regardless of how big the heap is. Now, one of the things that people often sort of make the assumption with when we talk about this kind of thing is that Zing needs a big heap. And the answer is it doesn't. So it does work very well with big heaps, and you can avoid the problems of where frequently you see people who break a big task up into multiple JVMs so that they can run with smaller heap spaces and avoid the problems of the pause times. But with Zing, you don't have to worry about that. So you make everything in one big JVM, one big heap, and it all works without any of the pauses that you expect for other algorithms that the JVM might be using. Let's talk a bit about GC tuning, because this is something that people spend a lot of time and a lot of effort, and therefore really a lot of cost in terms of trying to improve the way that the JVM works. And the reason that we do spend so long on this and so much effort is because there are lots of parameters and flags that you can change and set to try and affect the way that the garbage collector works. And so what I've done here is created a sort of like a diagram of lots of the different things that you have. There's literally dozens, if not hundreds, of flags that you can change to affect the way that the garbage collectors work, and select which garbage collector you want and so on. And so you end up with things like this. And these are two real-world examples from customers that we've worked with, where they've used a number of different flags to set up their JVM to try and get the best possible performance from it. Now, I don't want to talk through all the different things they've done here, but it is worth highlighting just one particular thing, which is both of these customers have set the survivor ratio for their application and the way that the JVM is going to allocate space in the heap. So one of them has set the survivor ratio to be 128. One of them has set the survivor ratio to be 2. So the question is, well, what's the right answer? Is it 2? Is it 128? Is it 64? Is it 17? It's probably not 17 because that's not even a number. But it's the idea that there's no easy way to say, okay, well, set it to this and you'll get this level of performance. It's very dependent on the profile of the application that you're running. And so what you end up with is a situation where you have to change the value and see whether it makes your performance better or whether it makes your performance worse. That would be okay if you only had one parameter to play with, but there's lots of different parameters and you end up with this sort of n-dimensional space where you're trying to change different things to find the best possible set of options that give you optimum level of performance. A set of flags used to tune the Zing JVM. Well, it gets nice and easy because there are no flags like that. Literally, all we say is that when you want to start using Zing, pick a heap size. And so just set the heap and run your application. The algorithm underneath will do all the hard work. It will figure out how to optimize, how to use the best possible way of doing things, and then deliver the performance you're looking for. What we do in terms of tuning is then to say, primarily what you're looking at is just tuning the size of the heap. So you kind of keep going down until you start to see performance fall off or you start running out of memory. And then you just kind of come back up a bit, give yourself some headroom and so on. To be fair, we do have some flags that we can use to tune performance even further, but there's literally about 5 of them. And we understand those quite carefully. We understand them quite well. So we know how to advise people to use them if they want to change the way that the system is performing. So primarily, just change the heap space and let the algorithm do its thing. Okay, so how can I show you that this actually works? How can I prove to you that what we can deliver with Zing through eliminating garbage collection pauses really does what I'm telling you? And to do that, we created this little open source tool called JHiccup. And JHiccup is designed to measure the latency associated with the JVM itself and everything below it. So the operating system, hardware, networking, so on. What it's not measuring is latency of your application. So it's not looking at how long it takes your application to process a transaction. It's looking at what is the impact of the JVM on the latency of your application. To do that, we run a thread in the JVM that's running your application, but it's completely separate. So it doesn't interact with your code. You don't need to change your code to enable it to work with that or anything. And to avoid the problems of Heisenberg's uncertainty principle, the act of observing something changes what you're observing, we want to minimize its impact. And most of the time, this thread is going to spend asleep. So when it starts, it will go to sleep for 1 millisecond. And when it wakes up, it will look at the system clock and it will say, I expected to wake up 1 millisecond later. What is the time now? And we can actually go down to quite fine granularity because we can use nanosecond resolution with the system clocks. And so we can measure down to nanoseconds of delay. If during that 1 millisecond, a garbage collection pause kicks in, you're running on, let's say, CMS, and you get a 20 millisecond pause, when we wake up, we'll see that we woke up 20 milliseconds later than we expected to. So we'll measure that, we'll record the data, then we can produce some histogram log files, which we can then produce some nice graphs of. And if we look at a typical graph here, what we've done is to take an application and run it on a particular hardware setup and a particular load that we've got. This is Elasticsearch running with a moderate heap. It's 128 gigabytes. And what we do is, first of all, we run it with hotspot, and then we run the exact same application with the exact same load on the same machine, just changing Java home to point at Zing rather than hotspot. If we look at the left-hand graph here, we can see what is a very typical graph for applications running on hotspot. So we see lots of spikes there. All of the small spikes there would indicate minor GC pauses. So the young generation needs to be collected. We see a small pause as that happens. All the application threads get stopped. And then we've got 2 bigger spikes there, which are going to be major GC pauses, where the old generation, something has to happen there, takes longer, so we see a bigger pause. So the graph here is measuring latency and higher means worse. So if we look at the right-hand side, which is Zing, you might look at that and go, ooh, that doesn't look very good. It looks like it's all sort of random and there's some big spikes there, and most of the time it's way above where the hotspot one is. And you would be very, very correct in your assumption there, except I've been very misleading here because I actually scaled the graphs differently, deliberately to mislead people. So if we look at the left-hand side, this is running hotspot, and the graph is from 0 to 8 seconds, meaning all those minor GC pauses around half a second, and the major GC pauses are something like 5.5, 6.5 seconds there. On the Zing side, I have scaled it from 0 to 80 milliseconds. And if I change the scale on the graph for Zing to be the same, we see the effect. So this is where it's like, this is the kind of thing you want to show your boss. This is great, because essentially we've eliminated all of the garbage collection pauses that you expect for the minor GC and the major GC pauses. So that's those half-second pauses, those 5.5, 6.5 second pauses have just disappeared. And if you look at that earlier one with the 0 to 80 milliseconds, a lot of that noise that you see there is actually not down to the JVM itself. What you're also seeing is artifacts of the way that the operating system works. So you'll see context switching happening there and various other things, hardware, cache misses and stuff like that, which will cause spikes in the latency of the application. But it's not down to the GC effect of the JVM. Just showing another graph. This time I have scaled it the same so that you get the effect. This is Hazelcast running on a smaller heap. So this is 1 gigabyte. Again, same machine, same application, same workload, just switching which JVM we had. And we can see here that with running hotspot, obviously there's something happening at the beginning in terms of allocation and stuff where we're seeing sort of spike up to just under 250 milliseconds. And then it goes into almost continuous GC pauses around 25 to 40 milliseconds. If I was looking at this for a customer, I'd probably say that they've done something wrong in terms of their setup for the heap, because it's probably too small. But even with that situation, if we look at the Zing side, then it again takes out all of the garbage collection pauses and we don't have to worry about that. So you don't even have to worry about trying to change the configuration. Okay, that's garbage collection. What about JIT compilation? So as I said, the issue that we have with JIT compilation is that there are sort of 3 phases to it. The first is we're not doing any JIT compilation, we're just running an interpreted mode. Second is where we're running C1 client compiler, fast warm-up, fast compilation, but without optimizations. And then you've got C2, which does much slower compilation, but much higher levels of optimization. And then we've got the time it takes to get from startup to our optimum level. So we looked at that and we said, okay, well, how can we get the most improvement in performance? And clearly trying to improve the interpreter wasn't going to work. Even trying to improve C1 wasn't going to buy us much, because most of the time, once the application's warmed up, you're not using C1 compiled code, and it doesn't really optimize anyway. So C2 was the answer. And we said, okay, let's replace C2. And again, we looked around and said, let's not start from scratch. What can we use that is already available? And we found there's this really good project called LLVM. And LLVM has been around for a long time. It's been around for about 20 years. It's a very heavily used compiler project with lots of contributors, people like Microsoft, people like Intel, NVIDIA, Apple, all sorts of people that understand about the chip architectures, understand about compiler technologies, are all contributing to this project. It's really primarily designed as a static compiler, and really the back end of the compilation process. So you're taking intermediate representation from your lexical analyzer and parser, and then taking that and optimizing it in order to generate the native code for your platform. What this allows us to do, because we took LLVM as a static compiler and we then integrated it into the JVM as a JIT, because essentially we just needed the code generation part of that, integrated it into the JVM, made it work with things like the garbage collector and so on, and then we contributed that code back to the LLVM project because we've got open source people. And this allows us to get much better performance out of the JIT compiled code. So things like better intrinsics, we can do more inlining, fewer compiler excludes, things like that. To give you some examples of that, here's a very simple piece of code where what we're doing is we're taking an array of integers and we're simply adding up the values in that array. If you give that to pretty much any compiler, any modern compiler, it will look at that and say, we can use vector operations to optimize this. And a vector operation is one where you have a very wide register and you load up multiple elements from your array into the wide register. And then in a single machine instruction, you can apply the same operation to all of those things in one clock cycle. So it's very efficient, single instruction, multiple data, been around for a long time. But if you look at things like the Intel processors, we're now up to AVX 512, meaning we have 512-bit wide registers. So there's lots of things you can do with that. So great, modern compiler takes that, optimizes it, wonderful. However, if we make the code a little bit more complicated and we introduce a conditional, so we're saying, okay, we've got two arrays now, and we only want to add the elements of one array to the other if one of those arrays is or one of the values is even, that gets a lot more complicated. Compilers will not recognize that and be able to optimize it using vector instructions, or at least most won't. Falcon will. And if we look at the code that's generated, this is taking C2 as our JIT compiler, and we look at the output of that in terms of the generated code. Don't need to look at all the instructions here, but essentially what we're seeing is the big red box is the loop that's being used there. And the two smaller red boxes indicates that the only optimization that's happening there is loop unrolling. And we're being able to do two elements processing for each iteration of the loop. It's a very minor improvement, but it gives a little bit better performance. If we look at what we get from Falcon, so exact same code, compile it on machine. This one's using a Broadwell E5 Xeon, and that one happens to have AVX2 instructions available, which is a 256-bit wide register. We see very different code. Now, the box looks a lot bigger, so you might think, ooh, lots more code, maybe it's not as efficient. But essentially what we're doing there is enabling the use of vector instructions, and we're doing loop unrolling, but in this case, we're doing 4 elements per iteration of the loop. And by using the wide register, we're actually able to process 32 elements per iteration of the loop. And most of those will be, was it like 8 of those will be done in parallel. So the overall effect of this is much more optimized than the code that's generated by the C2 JIT compiler. If you've got something like a numerically intensive operation, this is a great way of improving the performance of it. And it's worth pointing out this is just one example of the things that we're able to do with Falcon that we couldn't do with C2. We're looking at other things in terms of better escape analysis, more inlining, and as I say, intrinsics is another area that we're going to experiment with. One of the nice things about LLVM is it's very modular in its design. So it's easy, now we've integrated it into the JVM, to add new features to it. And the other thing that's really good for us is every time we rebase off the repository, we get all the things that other people have contributed. And so we pick up lots of improvements from them as well. Last thing to talk about is the idea of ready now as a warm-up technology. And if we think back to that graph at the beginning where we saw how long it takes to go through the different phases of JIT compilation, the real problem with that is not just how long it takes to happen, but the fact that whenever we start up the application, we have to go back through the same set of things. So we start off in interpreted, we have to recompile with C1, we have to recompile with C2. Ready now is about trying to eliminate that as much as possible. So what we do is we let the application run until it's warmed up. So all the methods that are frequently used have been compiled. We got to the C2 compiled code, or Falcon compiled code, I should say. We've avoided all the de-optimizations. Those have been compiled out. and we're ready, we can take a profile. A profile consists of 4 specific things. First is all the classes that are currently loaded. Second, all the classes that are currently initialized, because they may be different. Then all the profiling data that was collected from the C1 compiled code and was used as input into Falcon to generate its compiled code. And then all of those speculative optimizations that turned out to be wrong. So we had to throw away the code and then recompile it. So we keep all those 4 things. Now, great thing about that is we can gather that data over a longer time. We don't have to wait, okay, just wait a few seconds or maybe a minute. We could let the application run for a day. We could let the application run for a week. Doesn't matter. The other thing we can do is we can collect profiles at different times so that we can say, okay, well, we'll have a profile for Monday morning, have a profile for Friday afternoon, and that will give us a way, if we want to restart the application, we can do it using a specific profile to get us better performance for that particular usage. How we use that is to say, when we start the application, we look at that information in our profile and we say, right, immediately load all the classes that we can load from that list. Then initialize all the classes we can from that list. Then take all the methods we know need to be compiled, pass them to the JIT compiler with the profiling data and the fact that these are the speculative optimizations which don't work, and let the JIT compiler do all of that compilation before we get to the main entry point. That way, by doing all that work ahead of time, you literally have about 98% of the performance when you start your main application that you would have had when the profile was taken. You need something like 2 or 3 transactions just to kind of kickstart everything, and then you're up and running with that same level of performance you had when the profile was taken. So what that does is, again, improve the profile of the application from a latency point of view. And if we look at that, what we would see is that before using Ready Now, we see a typical graph here where we've got the orange line that shows different pieces of code being compiled, maybe some de-optimizations, speculative optimizations that fail, gradually warming up and then getting to our optimum level of performance. Blue line, using Ready Now, simply eliminate all of that problem and have a much lower latency for the application. Now, there is just one little bit of a downside to this. If we look at a sort of simplified graph of how the application looks without Ready Now, we've got our warm-up slope until we get our optimum level of performance. If we look at it with Ready Now, it's much better in terms of we've got a much steeper graph and we get to that optimum level of performance much more quickly. But there's this kind of blank section here where the JVM has to do all the class loading, initialization, and compilation before we can actually start running the main entry point. Now, we do actually limit that. So even if we haven't finished compiling all the code, we will start running your application at a certain point. We'll say, okay, after like a couple of seconds, we'll assume that you really want your application to start at some point. So we will try to eliminate that as much as possible. But what we've also done now is to think about how we could improve that even further. If we look at how the code that's generated by Falcon works, what we find is that we've got the bytecodes as our front end. Those get converted into the intermediate representation by the underlying JVM code, and that's what we pass to LLVM. LLVM then needs to understand how to optimize that particular method. And what it will do is it will send callbacks to the virtual machine with queries about how that method is being used. So it asks for information about the profiling data, and the VM will then give it responses saying, this is the information collected in the profiling information, so use that to optimize. LLVM will then take all that, generate the native code, and return that as a compiled method. That's all good. What we know about LLVM is that it is a fully deterministic compiler, meaning that if you take the same inputs, you're guaranteed to get the same output. And in terms of inputs, that means that if you take the same method, which has the same set of bytecodes, you don't change your method, don't recompile it, and you take the same profiling information, which means that the queries and the responses that are going to be used by LLVM will be the same. So that's our identical inputs. The produced machine code on the output will be identical. And we can use that fact. So now what we do is, in addition to collecting the profile in terms of the classes loaded, initialized, the profiling information, and the speculative optimizations that failed, we also record all of the compiled code. That way, we can put our compile stash, which is what we call it, put our compile stash between the JVM and the Falcon JIT compiler. So that way, if we find that we've got the same method that we're compiling and we know that the profiling information matches, so it's sort of like a fingerprint, then we can eliminate the need to get LLVM to do the compilation, and we can simply pull the information out of the compile stash and get that much more quickly because it's already been compiled. So we just take it out of the stash and give it to the VM to use. What that does is effectively shift the startup time and make that blank area much, much shorter. So we can reduce the compilation time by up to 80%. We can reduce the CPU load, because it's not doing so much compilation, by up to 60%. So it's trying to get us to the ideal graph. It's not quite there, but it's very close to that ideal graph of 100% right from the very beginning and 100% all the way across. So just to summarize then, essentially Zing JVM is all about starting fast, so using ready now to get the application running as quickly as possible, going faster, and so using Falcon to generate more heavily optimized code that gives you a higher level of overall performance, and staying fast from the point of view of avoiding those garbage collection pauses. Again, the key thing about this is it is a simple replacement for the other JVMs, no recoding necessary. One thing I probably should have mentioned earlier on in terms of the Zing system tools is that in the most recent releases of Zing, we've actually eliminated the need for Zing system tools. We now use some of the more modern system calls that are available in the Linux kernel to do much of the same thing that we could do with our own kernel module. And that way you don't have to install that unless you're using more than 1 terabyte of heap. If you're using less than 1 terabyte of heap, which could well be in a microservices environment, then you can just put Zing into your container image, deploy that. You don't have to worry about installing anything on the host, and you can use it in exactly the same way as you would any other JVM. That's been very popular with some of our customers. If you're interested in trying this, you get a free trial for 30 days, azure.com/Zing trial, and we will even help you produce some of those nice graphs, and you can show it to your boss and say, look, this is how it works. You know, look, we've just eliminated all of the garbage collection pauses that we spent years trying to get round. So that is basically the presentation. So I'm happy to take questions if there are people who have questions. So.
All right. Thanks, Simon, for that presentation. Let's open up the floor for anybody who has some questions around the presentation or garbage collection or JVM performance for that matter. I think Simon should be able to answer all those different types of questions, right?
I hope so.
All right, so does anybody have any questions, comments? Anyone want to talk about G1, GC? I don't know. There's lots of possibilities here.
I have a question.
In terms of, yes, go ahead, Rex.
Simon, thank you very much for your presentation. It was great. So my question is, how does this interact in Docker containers? Is there anything special we need to do?
So that's the good thing, as I said, with the more recent releases, because we've avoided the use of the Zing system tools now for less than 1 terabyte heaps, which I guess most microservices are going to be less than 1 terabyte, then you don't have to do anything special. So you can literally just create, we have Docker images of Zing already that you can either get from Docker Hub or you can get from our website. The only thing that I would advise is if you want to use ready now, then you just need to create the profile for the running application, and then put that into the image, so that when you start up the container with your application or your service inside it, then it can use that to minimize the startup time or the warm-up time of your application. So there's nothing special that needs to be done. In fact, it's simpler, if anything, because you avoid a lot of the command line flags that you would need to set up.
Thank you.
All right, more questions?
I got one. How does it compare with the Growl Vm?
Good. I was hoping somebody was going to ask that, because it normally comes up in the discussion. Yeah. So Growl Vm is a different approach to how to improve performance. And what they're doing is looking at much more the idea of native images. So that's ahead of time static compilation. And what they do is obviously take an application, and rather than doing just-in-time compilation, they will compile it ahead of time, so that when you start the application, you're running native instructions straight away. And that gives you very fast startup time, because it's like compiled C or C++. Now, the downside of that, there's a couple of downsides. One is that it's difficult to do all of the things that Java does if you do native compilation. So, for example, Growl doesn't support reflection. That's quite a big thing. And also dynamic class loading is a problem. So there's some restrictions on what you can do with that. But the other thing that's significant is that you lose a lot of the benefit of being able to do compilation of a running system. And the kind of things that you can do with a running system are things like method inlining, which is one of the most common techniques for improving optimizations. With a statically compiled piece of code, you're limited on which method you can inline because of the dynamic class loading nature of Java. So obviously with Growl, they don't support dynamic class loading, so they can get around that problem. But for most languages, if you want to use dynamic class loading, you can't do aggressive method inlining. The other thing is this idea of speculative optimizations. So what we found is that literally half of the performance improvements we get are down to speculative optimizations and being able to optimize, like I said, on the idea of a flow through a particular method based on its history and how it's used in the future. And that really does bias a lot. But you can't do that with statically compiled code. Now, if you talk to the Growl engineers, they say, oh, we've got this thing called profile guided optimization. And what they do is they say, okay, run your application and, like us, take a profile of the running application once it's set up. And then they use that as a feedback into their compiler. So it compiles the code based on how that application was run. But of course, that fixes it. So if the way your application works changes dynamically whilst you're running the application, then suddenly that profile guided optimization won't be right and it won't be able to adapt to it. Whereas with JIT compilation, if the profile changes and suddenly you need different methods to be compiled, then you can do that in a running system and have the thing adapt to the changes in the way that the application is being used. So there are some good things with Growl very much in terms of startup, but the overall, if you're looking at things that are longer running, then you tend to lose that benefit. The way that I see Growl as being beneficial is if you're doing things like serverless computing and Amazon, AWS, what are they? I can't remember the name for them. Thank you, Lambdas, yes, AWS Lambdas, yeah. So if you're doing that kind of thing where you're very short-lived, then that sort of thing, Growl is very beneficial to that. But longer running applications where you can see the benefit of the JIT compilation, Growl is not so well suited to that kind of thing.
Yeah, Simon, I think that Growl VM also has, aside from the inability to do long-term optimization, I think Growl VM also has a slight degradation in both memory utilization, i.e. that it uses more memory over time, and also a slight degradation in overall CPU performance over time. So instead of the application staying at, like in the first chart that you showed, which was the optimal, right? You just have the flat line. It actually gets worse the longer your application is running, and the more requests it's taking, the more objects it's creating, the more computations it's doing, etc. So that's something to be aware of with Growl VM also. But like you said, Growl VM is meant to be running, is meant for not so long running deployments of Java applications, right? We're talking about things that run for minutes or hours at most, and not days and days. So, yep. Okay. More questions for Simon? So some good questions already. So anyone got some more questions for Simon?
Also on the also on the Growl, it's also, there's like the other side effect is that there's no performance improvement with like file IO from Growl. So, one of the things, like you said, it's that fast limited time run, but even some of the things that we would normally think, oh, this will be faster, not necessarily. It's things that you have to experiment before you go the Growl path. Make sure how long is it going to run? How does it reach out to resources? How does it behave with that? It's the other questions you want to ask.
Yeah, good point.
Yep. Okay. More questions or comments for Simon? He said he'd stay up till 3 a.m. for us, so we still have him for another hour and a half.
So in terms of,
oh, go ahead, Hubert.
So in terms of the C2 compiler, I'm guessing that happens multiple times because you're querying the usage patterns.
Yes. Yeah. So it can happen multiple times. Yeah.
Cool. Is there a reason why? Is there a way to just set it so C4, you go straight to the C4 compiler at the very beginning if you don't mind waiting?
Well, that's effectively what we do with Ready Now. So we effectively go straight to Falcon. It used to be C2, but now it's Falcon. So we effectively avoid the problems or the overhead of doing C1 compilation because we've already got the profiling information. We can just do go straight to the heavily optimized compilation.
Okay, cool. Thanks.
All right. More questions, comments for Simon? Going once. Going twice. And gone. So Simon, tell us about the presentation that you're going to be doing at DevNexus coming up in a couple of months here.
Yes. I can't remember which one you selected.
That's all right. I don't remember either. So just having a quick look to see what we picked up. I don't believe it was the same topic, but let's go have a quick look and make sure. Yes, it was very catchy. So Simon is going to be doing why a new Java is not the new Cobol.
Yes.
So that's the presentation. So give us a little teaser or like idea of what folks should expect in that presentation at DevNexus.
Yes. So, I mean, one of the things that we see a lot is, people are always talking about the death of Java, aren't they? And the fact that Java is going to become, is going to decrease in popularity. And even this week, I wrote a blog post beginning of this week about the fact that the TOB index has said now that Java is in third place. So there's now C is number 1 and Python is number 2 and Java is number 3 in terms of popularity. And it slipped out of the top 2, which was, it's been in for the last 20 years. And so people often say that Java is going to become the new Cobol. So it's never going to go away, but less and less people are going to be using it. And so we're going to see a gradual decline in it. And so the idea of this presentation is show people that there's a lot going on in the world of Java. And the fact that we now have the 6-month release cycle is leading to more features being added to the language faster than ever before. and there's lots of really cool things coming through, and trying to keep up with that is quite difficult. So what I'm going to do is I'm going to go through a sort of like a whirlwind tour of all the new language features that we've seen basically since JDK 10 up to, I guess it'll be JDK 16 by the time we get to the presentation next year. And so talk about all these things like records, talk about sealed classes, hidden classes, local variable type inference, lots of things like that that are adding these nice little features to Java to make it still fresh and still addressing some of the issues that people have had with the language in the past, and so kind of keeping it up to date and making sure that people still want to use it. So that's kind of what I'm going to do.
Yep. So that should be a lot of fun. One thing I always find a little annoying about all those surveys or whatever stats they come out, the TOB index on this, is that they always give it as a percentage, right? So it's like, it's like whatever, 38% of developers use JavaScript, X number use Python, X number use Java. But if you dig a little deeper and look at the actual numbers, you will see that there are actually more people using Java today than there ever have been. And you might be saying, well, how could that be possible? It's because, well, there are just a lot more developers today than there were a year ago or 5 years ago, 10 years ago. So in fact, there are actually more Java developers today than there ever have been before, even though it's quote unquote number 3 behind Python on those various indexes, right?
Yeah.
So.
Yeah, I mean, the TOB one is a little bit, because when you start looking at how they measure this thing, and TOB is very simplistic. It basically just looks at 25 different search engines and goes name of programming language plus programming, and just counts how many hits it gets. So there's no kind of like breaking it down into real sort of usage. It's just how many people have got pages up on the web that reference a particular programming language. People like RedMonk do a better job, I think. They do more of an analysis of usage and look at things like Stack Overflow questions and Reddit posts and job postings and stuff like that. So I find RedMonk is a better sort of trend indicator than maybe the TOB one.
I don't think, it's not just that. I think it's, you've also got to consider the, why the language is being used. So, I can't see anybody writing a credit card processing system in Python.
No, that's the thing, isn't it? Yeah.
So.
Yeah, I mean, one of the things they've said is that Python is very good at being able to knock up applications quickly, and that's why they're using it a lot more for sort of teaching comp sci in universities and things like that. So my son is learning Python at the moment, and I'm having fun learning Python with him. And it's one of those things where you as a real kind of, I will say I'm a kind of dyed in the wool Java person, and I playing with Python and things don't work, and you go, well, that's so obvious. Why doesn't it work? Because it doesn't have really nice typing like we have in Java, and you create a variable and you can't see what type it is because it's not not explicit, and then you try and use it and you find out that the Python runtime has decided it's one type and you expected it to be another type. So, but I'm going off on a tangent. And
speaking of Python, Guido van Rossum is now working at Microsoft.
Yes, I know. I saw that.
Yeah. I don't think he's necessarily working on Python, though. I think he hasn't decided or something. Yeah. Well, in terms of Python, it's a great language and everything, but I still don't trust people who like white space aware language. It's just me, maybe. But it's the whole white space aware thing. Every time I try to do Python, it drives me insane. I'm not sure why. Maybe it's from all those years of doing Turbo Pascal or whatever. But anyways, it's like, white space is not significant. Not how it works. So anyways, all right, more questions or comments for Simon before we start wrapping it up here? Nope. All right, I think Vincent already mentioned that we still have about 50 swag boxes available for DevNexus. So if you sign up soon, you'll be able to receive one of those. Simon will be speaking there, and we have a ton of other great speakers. We will hopefully soon be making an announcement about the keynotes, and there's some exciting news around that, which hopefully, if everything works out, we'll be able to share with you in the next few weeks. So anything else from Burke, Glenn, Vincent, anyone else from the Atlanta Jug board want to say anything else before we sign off for the evening?
Stay safe, folks.
Thanks for being here.
Yeah. Well, I know
Yep.
Simon wants. Simon's just about to go clubbing because this is now clubbing time in London.
He's locked down.
Lockdown. Yeah, can't go out.
It's never stopped us in the past. We went through 2 wars, remember? No. But we'll keep the Zoom channel open and just chit chat if you want to hang out. I know I'm going to hang out and say, make fun of Burke, so you guys can help.
Yeah, I'm actually going to go to bed because I've got a webinar to do tomorrow morning.
All right, man. Well, we appreciate it, brother.
Thank you.
Okay, great. Thanks a lot.
Cheers, Simon.
Thank you.
Yes, now we can talk about him.
Gossip begins.
Exactly. All right. Is everyone sick and tired of the pandemic and being imprisoned at home already, or is it just me?
It's bad when you start reading up on what's the side effects of the vaccines. Okay, day one, first one's not so bad. The second one's really bad side effects. Like, I'll take those side effects. I have a big sign right here. Vaccine here.
We're not even going back to my work.
Yeah, right here. It's like right there, right on. You said a big white spot right there.
We're not even going back to my work until June.
June.
Okay, so your workplace has said that they might let you back in to the office or ask you to come back in the office in June. Is that right?
Yeah.
June.
Yeah.
It's a long.
Yeah, that sounds about right. Time. Yeah, with the tentative timetable that NSAID and some of the government officials have said, it looks like as the vaccine starts rolling out in March and April, we might be able to have a JUG meeting like in June. That would be wonderful, wouldn't it?
Woo.
I know. I mean, sorry, an in-person JUG meeting.
Actually,
yes.
I talked to Rome and I. Because they owe us for the entire year because we prepaid it. So I think I already talked to them about dates from June onwards. So we have them.
Nice.
Cool.
I think there might actually be a possibility. Maybe even earlier. We'll see. But we'll have to come up with a way to verify that people have been vaccinated before they can come. But
well, we could just look. Everybody gets a hazmat suit, and then we could all hang out. That'd be pretty funny,
dude.
Wouldn't it?
It's hard to eat chicken wings with a hazmat suit on. That's all I'm saying.
There's always a way. In fact, why don't we do that? If anyone has a hazmat suit and they want to have an AJUG meeting, we'll do a hybrid event. How about that?
There you go.
I've already I don't know about y'all, but the first presentation I give in person, what I'm going to do is just come out with fluffy bunny slippers on, and I'm going to put a camera on the podium, have a code.
This is how I've been practicing for the past 6 months.
Yeah, I'm in this getting back into the real world part. Put on my headphones.
Just make sure you got this.
Say, what is this? This is business casual, right, guys?
Exactly. When I share with this group, but I think I've already told the JUG guys, for DevNexus 2022, my tentative tagline is back with an MF and vengeance.
That's right.
So for those people who are interested, we're looking for volunteers for 2022. This year, you get a break. No volunteers for DevNext 2021.
I still think we should sign up about 50 volunteers, Glenn, just for shits and giggles.
It's the training. It's a tough training we put people through.
How come you guys decided to just do one day on DevNexus?
Well, people are, So do you really want to spend 2 days staring at, I mean, you stare at a screen all day anyway. Do you really want to spend 2 days doing it? It's just tiring, man.
2 days on the Asterisk conference.
The what, sorry?
Right after.
Yeah, there's been plenty of conferences that run over look, AWS reInvent is running over 3 weeks. You know, it's just the main reason for doing it, that is just to, you know, it's getting some great content out to the community. It's not about having a big event that, you know.
Yeah, I think what Vince is trying to say is that there's a fair amount of Zoom fatigue, and we felt like we felt like people would be willing to commit to most of one day to like go to a virtual event, and you know, doing like 2 days was like that may be pushing a little bit, because you know, if people don't you know, people just don't have the Zoom fatigue or can't get time off work or just don't want to do it. It's like, well, let's find a happy medium where we can just do 1 day, and hopefully people are willing to say, yeah, I'll take that day off of work, or let me rephrase that. I will tell my boss that I'm doing training on this day and come to the conference and hang out with everyone. So I think that was our thinking behind just doing 1 day. So.
That's fair enough.
We will have we'll have 5 concurrent tracks though, so there'll be plenty of content, and you'll be able to watch all the videos pretty shortly after the event. So you know, if you want to do 2, 3 days or 5 days for that matter, you could watch all the content and you know, take up taking all the new stuff. We have some pretty good stuff lined up, and a lot of unique content. One of the challenges, Scott, around this was that since everyone is doing virtual events, there's not like a lot of unique content. Like a lot of stuff is already out on YouTube, or someone did it at this other conference, or someone did it at a meetup or whatever. So we asked the speakers to provide content that they have not done before DevNexus. So we'll have a lot of good, unique content. But again, that was part of the challenge and part of the reason why we slimmed it down to 1 day, so that we have 1 day in 5 tracks of all unique content. Well, not all, but mostly unique content.
And
we said that any new technology couldn't start with the letter K. I think that was one of them.
And we've tested this format before, and we'll have a Zoom instance running for each track all day long. Yeah. So what we've done in the past, and what we'll do at DevNexus, is after their recorded session is finished, the speaker will be on here like this, doing Q&A from, you know, whoever wants to ask questions. And the rooms will, you know, they'll take up to 300 people. And you know, not all 300 people are going to ask questions, but they can listen and watch, and, you know, a handful of people will ask questions, and the conversation will continue as like almost a quasi hallway track.
How long do we keep in the hallway for?
Yeah, exactly like we're doing now. But it will be like this running all day. And there'll be like one for Java, one for cloud, one, you know, and so on and so on for security, and so on and so on. And this has worked pretty well in the past for us. At another event we tested it at.
Yeah, I was at I did a talk at Spring One, and after the talk, I was in the hallway track for about 45 minutes, almost an hour after, just answering questions and talking with folks. It's not like the same as being in a conference talking to the speaker, but in some ways, a lot of people are really comfortable just asking questions through text versus, you know, in person, and the questions were magnificent. So I take advantage of those hallways. The speakers look forward to that. I know I do.
Yeah, and actually the hallway track at DevNexus will be, it'll be over Zoom. So you could flip on your video and you'll ask a question via text or chat if you like. So it's not the same, as Glenn said, as being in person, but until they make VR technology really good, or we get like the Star Wars like hollow projection devices, which it's 2020. Where are those things, right?
Yeah, we'll be sending everybody an Oculus Rift.
But you have to provide your own bucket if you get nauseous.
Yeah.
Yep. So. All right. All right, folks, I got to jump off. I got to eat
same
something
here.
before I
Folks.
pass out from low sugar. But it was good to see everyone. Don't forget, next month we have Venkat doing our JUG meeting. So as you know, he comes every Christmas. So he'll be here for Christmas.
Like
And the
Santa.
micro profile workshop in a couple of weeks as well. So I'd encourage you guys to do that if you can spare the time.
You know what? The one thing I'm looking forward to on this Venkat talk, I don't have to sit outside. Because every last 3 years when Venkat comes to talk, I have to sit out. I had to sit outside. Even though I got in early, I was like, okay, I'll let people come in, and then I wound up sitting outside the door. So I'm looking
Apparently
forward
you're
to actually
outside.
seeing his face. What was that?
Apparently you're outside right now.
Well, you know, but I'm looking at you in the face. Not. Well, actually, I'm seeing your profile too. So maybe this is not working like I expected.
But Glenn's not on his kayak though, so that's the difference.
Oh, that's true. That's true. I can paddle around. All right, folks. Have a wonderful evening. Thank you for
All right.
coming.
Have a good evening, everybody.
See you.
Bye, guys.
Adios.